Okay, so now that we have taken a look at matrix notation and kind of what all this stuff means when we look at the system in matrix form, I want to talk about one method for solving these, which is called straight line solutions. So I'm using the same example I used in the previous lesson. That's okay, I'm not going to go back up to it, but this was a linear system with constant coefficients. I've got a sketch here of the vector field, and I want you to pay close attention to what is happening with the arrows. That's the part that really tells us what's going on. Do you notice, and it's hard to tell exactly, especially if it's in black and white on your paper, but just kind of roll with me here. Do you notice that there's along the x-axis, you've got arrows that are going out? So they're going away from the origin. And then along this other line right here that they've drawn in, the graph, all the arrows, notice, are going towards the origin. So there's a little bit of behavior in terms of which way the solutions are moving, or the vectors are moving rather. So we can say, let's just jot those two ideas down. We can say that there are two lines in the sketch, and we notice that for the one line, so the one line, and I'm going to make a note that that's the x-axis, that your vectors are moving away from the origin. And then for the other line, let's say the other line, I'll explain this a little better here, but all I want you to look at is what's happening. So the other line, the vectors are moving towards the origin. Sorry, I didn't leave you much room here. Okay, this is important because this tells us the coefficients for those lines basically are going to tell us or help us find a more general solution. In the previous section, we saw that y1 equals e to the 2t0. That was a particular solution, and y2 equals negative e to the negative 4t, and 2e to the negative 4t was another particular solution. So how does this relate to the vector field? So here's the part I want you to kind of catch. Let's start with the y1 solution. Well, if you'll notice that y1 particular solution represents a vector along the x-axis. Okay? And think about kind of what I'm saying here. Let me clarify this. Along the x-axis. Let's suppose t is 1. Okay, so maybe don't write this, but just kind of go through with me. Let's suppose t is 1. That would give us a vector of e to the second comma 0. Well, remember, that's your x component, that's your y component. That would mean I am on the x-axis and I'm moving in the positive direction, e squared units, and y is 0. And that's what we're seeing here. Suppose t equals, I don't know, let's say 2, we would have e to the fourth comma 0. So when t is 2, that gives us vectors. Notice they're going to get longer the further away we go and the larger t gets. So that first solution represents the vectors that are along the x-axis. Now the second solution, it's a little harder to see right away, but it actually does follow a similar pattern, because the second solution, you'll notice, is a vector, or represents a vector along this diagonal line. So let's write that down. So y sub 2, the particular solution, is a vector along this diagonal line, and you may not can tell just by looking at it, but the equation for that diagonal line is y equals negative 2x. So pause for a second to make sure you see that. That would be the line that has a slope of negative 2 and cuts through the origin. That is this line right here. So what we can do then is we can write both of these as vectors with positive scalar multiples. So let me show you what I mean by that. So y1 is equal to e to the 2t and 0 are your components. And so we can think of that as e to the 2t times 1, 0. So that would be your positive scalar multiple of 1 and 0. The other solution, y sub 2, we can write, notice they both have e to the negative 4t. So if you kind of think of it as like factoring, take out e to the negative 4t, and that leaves me with a coefficient of negative 1 and positive 2. And again, that would get you solutions or vectors along this line, and that's what we're talking about. So these are called the straight line solutions to the system. So let's elaborate on that a little bit. So if we know that matrix A, that coefficient matrix, has a real eigenvalue, and I'm not sure that we have talked yet about eigenvalues and eigenvectors. Hang in there, we'll get into what this means more and more as we go, so just go with me for a second. The eigenvalue, we would call that lambda, and it would have a corresponding eigenvector. So this bold V, remember, is the eigenvector. Then the solution to the system, dy dt equals ay, will look like this. So we're going to say the general solution would be y is equal to e to the lambda t times that eigenvector. So what we found up here, this 1, 0 and this negative 1, 2, those are really eigenvectors for those solutions. If lambda 1 and lambda 2 are distinct and real eigenvalues, because we'll have some other scenarios later, but right now, if they're distinct and they're real eigenvalues with their corresponding eigenvectors, then particular solutions would follow this format. Same format. It would be e to the lambda 1 t times the eigenvector for that one, and then the other solution, y sub 2, would be e to the lambda sub 2 t times that corresponding eigenvector. They would be linearly independent particular solutions, and we know that if we put those together from the last section, that linearity principle that we talked about, our general solution could be expressed as k1 e to the lambda 1 t times the eigenvector for that one, plus k2 times e to the lambda 2 t times the eigenvector for that one. And that would give us a way to find our general solution to the system using these straight lines, because those straight lines are going to help us find those eigenvectors that we need for the solution. All right, so let's talk a little bit more about eigenvalues and eigenvectors. And if you haven't taken linear algebra yet, that's okay. You're going to learn this a little bit more detail, what this means specifically in linear algebra. But for our purposes, here's all I need you to know. This lambda is called an eigenvalue for a given matrix if the determinant of the matrix A minus lambda and B and C and D minus lambda. So if the determinant for this specific special matrix equals 0, that means that lambda is an eigenvalue. Now, how do we get determinants? I think we've talked about this, but to get a determinant, let me just remind you, let's say I have A, B, C, D. The bars mean I'm taking the determinant of this 2 by 2 matrix. That would be found by doing the product of A times D minus the product of B times C. So how does that apply here? Well, it would be A minus lambda times D minus lambda, and then minus the product of BC. And we would set that equal to 0 and solve. Basically, it's a quadratic equation is all it is. That will give us the eigenvalue that we would need for that particular matrix. So the eigenvector that's associated with that given eigenvalue would be the vector such that, so if we're talking about matrix A was the coefficient matrix, it would be A times the eigenvector would just be lambda times the eigenvector. And we're going to use this to help us find these solutions. And I know this is a little confusing right now. Just hang in there. Let's do some examples and put this all together. Okay, so first they want us, here's our system of differential equations. They've written it in matrix form, and they want us to find the eigenvalues first. All right, so let's note a couple of things. So our matrix A, our coefficient matrix is the 2, 2, 1, 3. So to get the eigenvalues, I'm going to use this definition that I have up here, and I'm going to just take the determinant of the matrix 2 minus lambda, and then 2, and 1, and then 3 minus lambda. And that would just be 2 minus lambda times 3 minus lambda minus 2 times 1, and we're going to set that equal to 0. So that would give me lambda squared minus 5 lambda, and then we would have plus 6 minus 2, which would give me plus 4. If we're lucky, this factors, although it certainly doesn't have to. We'll have other scenarios where we can handle it if it doesn't, but for now it does. We've got lambda minus 4, lambda minus 1. So my two eigenvalues, I'm going to call it lambda 1 is equal to 4, and then lambda 2 is equal to 1. So those are the eigenvalues associated with this system. So let me go ahead and take a look at what the associated eigenvectors would look like. All right, so I'm going to start with the lambda 2 equals, lambda 1 equals 4. And I'm using the definition up here of what an eigenvector is. So an eigenvector means that the coefficient matrix times the variable matrix should equal to lambda times that variable matrix. So that would be, in this case, my coefficient matrix was 2, 2, 1, 3. And we know that times xy, that would equal to the lambda, which is 4, times xy. All right, so here's where you're going to get those straight line solutions. I'm going to take that 2 and I'm going to go ahead and multiply this out. So we're going to have 2x plus 2y should equal 4x. And what I want you to do is rearrange this so that you have y equals a function of x. And it's going to just be a linear equation is what it's going to be. I'm going to subtract the 2x. I have 2y, of course, equals 2x, which means that y has to equal x. And I'm going to highlight that because we're going to come back to that in just a minute. And then, now listen, I used the x component to do that, but we could have just as easily used the y component. So your other option, I could have done the same thing over here. I could have said 1 times x plus 3y, so using the 1 and the 3, that would equal 4y. And then do the same thing. If I move that y to the other side, that 3y, for example, to the other side, I end up with x equals y. Notice that you get the exact same thing. So whichever one you use is fine. Use whichever one seems easier to you. All right, so then what you're going to do, your job now that you have that straight line, is the equation rather for the straight line. Remember, that straight line y equals x, that was the equation we had back here. This is different, but it was same idea. So we're looking at a line, and I want you to come up with a vector along that line. And there's lots of different ways you could write this, but let's just pick something real basic. So if my equation, I know that I want it to be along the line y equals x, so I want my vector to follow that direction, then I'm going to write my vector here. So my vector 1, I'm going to call it, is equal to, if x is, like I said, pick something easy. So suppose, let's let x equal 1, then the x component would be 1, and then the corresponding y component would also be 1. You could use any multiple, though, that still falls along that line. I could use 2, 2. I could use 3, 3. I could use -1, -1. It doesn't matter. Just pick something basic. So my vector component for that given eigenvalue is 1, 1. All right, so now I'm going to do the same thing for my other lambda. So my lambda 2, remember, was equal to 1. So we're going to write 2, 2, 1, 3, and then times the xy again has to equal 1 times xy. And then we're going to write that out as a linear system. So I've got, and again, you can use either version. It does not matter. 2x plus 2y equals x if I just use the x components. That simplifies to y equals -1/2 x when I solve for y. So that's going to be the straight line solution for this eigenvector or eigenvalue. And so a vector that we could use for this would be, you could use anything you want. Like if I let x equal 1, I could use, if x is 1, the corresponding y value would be -1/2. Now my recommendation is choose a value for x that gets rid of your fractions. So suppose we let x equal 2, for example. the corresponding y value would be -1. So that's the eigenvector I'm going to go with for that part of the solution. Now, I'm running short on time for this video, so I'm going to pause this video and I'm going to have you watch the next one where I finish up the solution here.